Well, Ray gave us a good start because I'm going to start where he began, or he ended up. And I'm going to take Giant Fields through the present time, and actually, soon to come out is this new volume called Giant Fields of the Decade, 2000-2010. It'll be out this year. We don't have an exact date yet. So, this is an outgrowth of the work that Charles and I did in preparing this new volume, which actually is a continuation of the volumes that were started in 1970 by Mike Halbody. So why do we study giant fields? Well, first of all, as we know, they contribute to prosperity. It's also a vehicle for major wealth transfer between countries. They provide significant infrastructure with economies of scale, so that smaller developments can now become economic. Global supply, let's see how can I do this? Global supply tracks giant field output. As a matter of fact, since the 1960s, giant fields contribute about 60% of the global oil production. Giants, once they're found, keep getting bigger. Here we have a plot of years since discovery versus EUR for a number of California fields. And probably the best example is Midway Sunset, which started out somewhere down in this area in year 0. And in the last 100 years, it's now produced over 2.7 billion barrels. So the giants keep getting bigger. And finally, and very important for us, is they provide insights into petroleum systems. Insights we might not have otherwise, and we can use these insights in our exploration and development programs. So what is a giant field? A giant field is anything over 500 million barrels, as we've defined it, and there are about 957 of those in the world today. Significant supergiant fields are over 5 billion barrels, and there are about 97 supergiant fields in the world. And then we have the category megagiant fields, which are in excess of 10 billion barrels, and there's 7 of these in the world in our database. So we know the giant fields exist. We know they're important to us. What about the future? Are we going to be able to find more? Well, first of all, what's required, I believe, is open access to exploration, and these are in remote and challenging areas usually, and those issues may be political, they may be environmental. And we've been moving into a period of technological integration. Historically, explorers, and Steve Getz came up with this terminology, the rockers, the trappers, the sealers, and sources. The rockers, they understand the reservoirs, have a good picture of the reservoirs. The trappers, the geologists and geophysicists, who can map the geometry of the trapped well. The sealers and sourcers, these are the people who started with the source rocks and took them to the trap and sealed the hydrocarbons. So what is this technological integration all about? It's the ingenuity of the combined disciplines of geology, geophysics, and engineering, particularly. So what has really driven this process is big data. You know, Exxon recently said that they can harness the equivalent of 22,000 computers to do their processing. And so what we're seeing today with our projects is parallel processing. We're seeing neural networks being applied to these big data issues. We've developed ways of understanding reservoirs from the micro scale to the macro scale. We've gotten much better at reducing the uncertainty of the traps, the geometry of the traps. We can map the high migration paths better than we ever have before. On a geochemical basis, we understand the source rocks now and the origin of hydrocarbons and the generation of hydrocarbons, so we can predict these things. And then finally, and very importantly, we have significant advances in drilling and completion practices. So here's where we got our data to start with, and the project and the talk today is sort of an outcome of this material. So we started with a database of over 1,000 giant fields, and Mike Horn had been putting this together for a number of years before he passed away recently. We had IHS support, and that support was very important to us, particularly with the help of Pete Stark. We have the AAPG archive going back 100 years. This is all in data pages. It's available to everybody. And within that data pages database, we have the pre-existing Giant Fields Memoirs, and as I mentioned earlier, we're soon to have this one. So where are these giant fields? When were they found? Bill DeMis has come up with an interesting way of grouping in year baskets, if you will, of giant fields and exploration. His baskets are the U.S. dominated exploration, global expansion, post-World War II growth period, OPEC and nationalization, globalization and mergers, and emerging countries. In the graph here, I have the numbers of giant fields discovered. That's a lot easier than trying to deal with EURs for each of these. It's more consistent. And then the colors represent different parts of the world: North America, Eastern Europe, Central and South America, Africa, Middle East, and so forth. So starting where Ray left off, North America dominated the giant field discoveries. Following World War II, we suddenly see the USSR, the Middle East, and Africa. They become important to the discovery of giant fields. That continues up until about 1990, at which time the number of giant field discoveries has tailed off. And what's become very important here in this last period, called emerging countries, but we also have the unconventional revolution that has occurred there, and that's driven some large accumulation of discoveries. So is oil price, what does oil price have to do with giant field discoveries? The numbers, absolutely nothing really. This plots the oil price in 2014 dollars, the nominal oil price adjusted for inflation, and then Bill DeMis has this other price that he calls the real global price. It's adjusted for U.S., the value of the dollar. In red behind here, I've got the number of giant fields. So early in the late 19th century, we have a very wide fluctuation of price. That is stabilized with the Standard Oil Trust first, and then the Texas Railroad Commission proration. So the prices were reasonably stable through this period. And you can see that the discovery of giant fields really peaked during that period of reasonable stability in oil price. Following OPEC in 1973, the price spikes. When the price spikes, we get more drilling. We didn't discover more fields, but the price collapsed. And we'll talk about that in a minute in a little more detail. And then the price goes up again and down. And this is a period where it's from stable prices and long-term contracts into futures trading and the spot market. Well, as part of this, we had to consider what are the technologies being involved, when are these technologies occurring, when are the big advances in technology. So at the bottom here, we have the baskets I talked about. We have petroleum system concepts at the top. We have geophysical, petrophysical drilling and completion technology. I'm not going to go into a lot of detail on this, but so we have seeps and anticlinal traps, stratigraphic traps coming in 1930, development of seismic and the evolution of seismic data, evolution of petrophysical tools and combined tools. An important point in here is the advent of the computer and computing power that changed the world. And then we have our drilling and completion technologies, including stimulation and horizontal drilling. Well, one thing to note with this green background, which is the oil price, you see we have a sudden increase in technologies occurring during this time. And actually I attribute that to the fact that the price is low, We've got to get better. Otherwise, it's not economic. So the first period was here in the 90s. I think we all remember that. Some of us are old enough to remember one or two before then. And then we've got this latest one. Here's the peak. Here's the latest one. This is the advent of the unconventional revolution. And why is that? All these other developments are continuing and getting better and contributing to it. We have the critical element here of being able to drill and produce much more efficiently over long distances of lateral wells. The next series that you're going to see is an animation. I put this in because it's actually kind of fun to watch it work. This is Giant Fields of the World by decade. All of the gray circles on here, these gray circles are giant fields. Giants and supergiants and megagiants. I've highlighted supergiant fields in yellow, so you'll see when they come into the picture, and megagiants in blue. So I'm going to run this. And starting at about 1850, we've got to 1900, we have 11 fields. You can see it's primarily North America. That continues up until the post-World War II era. Again, North America, South America, through 1930. In 1930, in that decade, we start to see an expansion globally. That expansion dies down during World War II, and then expands again following World War II. In the 1960s, 22 fields developed. 1970s, and many of the fields developed. And the numbers of fields drop off, but we're still finding giants and supergiants. And then finally, in 2001 to 2010, what's happened is we've developed our seismic, our geophysical capabilities sufficiently. We can now see in subsalt. So where do we see significant activity? Offshore Brazil. We see a significant activity offshore West Africa. We have new discoveries in Madagascar. This is how we're getting into this emerging countries perspective. Madagascar and the Mediterranean Sea discoveries, as well as discoveries in the Gulf of Mexico in the subsalt world. So let's go back now and look at each of these time periods. So starting out with the early U.S.-dominated exploration up through about 1925. So prior to 1900, we had seeps. This is a nice oil seep in Colombia, incidentally. And then we had the development and the improvement on the anticlinal theory. So Charles had me put this in, the obligatory structure, map, and cross-section, and we can move on from that. Finally, let me use this picture. And so we had surface mapping of anticlines. We had the first seismic in 1D, and actually in 1921, reflection. They figured out how to do reflection seismic. There was a first resistivity tool. And then we had cemented casing and rotary drilling coming in at that time. 1926 to 45, a period of beginning global expansion that is actually reduced somewhat during World War II. Again, a lot of many discoveries in North America, South America, and of course the World War II interrupted this entire area as well as this area. So this period of global expansion, 1928, the first field was identified in terms of the structural trap by reflection seismic in 1928, and that was in Oklahoma. 1930, we have the recognition of stratigraphic traps. This is the East Texas field. This is the pinch out of the Woodbine, and you can see it here in cross-section. Recognition that oil deposits could occur offshore, 1938. Evolution of petrophysical logs. But here, I think even more importantly, was the publication of Archie's laws, when we can now actually describe the reservoir in more detail without actually having a complete suite of rocks in her hands. We had the diamond bit, the three-cone and roller bits, also developed during this time. 46 to 70, post-World War II growth, worldwide. Here our petrophysical laws continue to evolve. We move offshore, really offshore, 10 miles off Louisiana. This is also the time of the first hydraulic stimulation license that was issued to Halliburton by Stanley. 61 to 70 is critical because now we have digital computing in our big mainframes. We all remember those, I think. That enables our 2D seismic processing, log analysis, data management. And Mike Forrest and his buddies at Gel described bright spots in 1965. What am I stuck? Here we go. The next period, up through 1987, again worldwide. This starts with the oil embargo. Our processing now moves into workstations. We can see our seismic data in color, seismic stratigraphy. We begin to understand and picture the reservoirs in the subsurface. 3D seismic emerges. Now, this was an interesting fact to me. In 1977 was the first logging truck equipped with a computer. That wasn't that long ago. The evolution of the sonic tool helped us with our interpretation of seismic and processing. The next period, up through 2005, not much going on in North America at that time. We're improving on our seismic attributes. Horizontal drilling and stage fracturing are initiated. Because of our imaging capabilities, we get our first subsalt discovery, and the first dual activity drill ship facilitates deep water drilling. On this one? Yeah. Okay, emerging countries. Again, that's a global picture. Seismic technologies continue to improve. Our processing capabilities are improving. Subtrough drilling becomes common, and what are they drilling for? They're drilling for turbidite plays in deep water, and that's where much of the activity has been over the last few years. And at this point, very importantly, the source rocks become reservoirs. Horizontal drilling, multi-stage fracs, microseismic all facilitate this. So I'm going to finish up here with Mike Albuty. He described why giant fields are important because they help us understand the traps, the reservoirs, the source rocks, and so forth. But I think the most important part of that is that we should ask ourselves first, what is usual about each of these accumulations? What is unusual? And then we must concentrate on the unusual, for commonly it's the unusual aspect which is the key to the accumulation. Where have we been? This is the Global Fields database. And the journey continues. This shows the giant fields, and you can see now that I've included a number in this decade in North America of the shale plays in Argentina. So the search is continuing. Giant fields will continue to be found. The journey continues.